today. At this point, we've talked about functions. Functions are in terms of x, and so you'd have f of x is equal to something x, like 2x. And then we also did parametrics, and parametric is where we had x in terms of t and y in terms of t. And both of these usually generate this x of, and then the second one would be like a y, which is f of x, and this one would be x and then a y. And this will be the third type of equation that we can graph. Each of these are important because you can graph different equations. And in engineering, when you want to be able to mimic something that you're making, you want to have a mixture of things that you can graph. So you can make things in 3D. Some things in polar you would be able to graph that you couldn't in the other two. And so instead of x's and y's, we're now going to be dealing with r's and thetas. And that's going to be the polar system. And so we're going to be looking at these two variables. This r is called the directed distance. And theta is just the angle from the positive x-axis. This is going to be the new framework, and we're going to have new graphs that are in your packet that you can write on if you find that those are useful. It does tie in a lot of trigonometry that we've had in the past, so that's why we have that review packet, and we're filling in your different table with degrees on it, as well as your two triangles. Now, along with this, the other part that is going to be extremely important today is going to be knowing your 45, 45, 90 triangles and your 30, 60, 90 triangles. And if you can work around these two triangles, I think you're going to find that this is an easy section. If you don't, it's going to be longer and a little bit more cumbersome. So we're going to remember the 1 is opposite to 30, the radical 3 is opposite to 60. You're always going to reference the short side here in going to the other two on the 30, 60, 90. And so with that in mind, you're going to see that you have the same diagram that we've had in the past. And you're going to notice that you have an X, you have a Y, you have a triangle there, and this right here is your R, which is your directed distance. This R theta that we've had in the past is the same R theta that we're talking about with polar coordinates. Except R now has a name, which is directed distance from the pole, and that's going to be called the pole instead of the origin, because it's polar graph. Well, what do I know about this in terms of equations? Because you can do these exercises today by one of two ways. You could either work with the special right triangles, 30, 60, 90, and 45, 45, 90, work around the triangles after you draw it, or you could go to equations and do a conversion with the equations. And this would be converting from the function xy to the polar graph r theta. So what are those conversion equations? we're just going to get these off of here, which we've had before. X squared plus y squared equals r squared. Tangent of theta is equal to y over x. And the last conversion is going to be, the two more, sine theta equals y over r, which means r sine theta equals y, and cosine theta equals x over r cosine theta is equal to x. So these four are ones that you can use in your conversions as we start going through this. All right, so I have equations that I can go between, and you can see again, x and y to r, theta to y and x, r and theta to y, r and theta to x, converting between polar and rectangular form. And these are the same formulas that we just created. So in this particular section, it's a little bit hard to go through the concepts and then do the problems. So we're going to do the problems at the same time as the concepts as we go through. The first thing that we want to do is be able to draw a point on the polar graph. This polar graph is the same idea as the polar graph that you have in your packet. Notice a couple things about this. This now is a pole at the middle. It's going around just like the unit circle with your angles. That's not different. And then you have something called concentric circles, which means with the same center. But with those concentric circles, you count the circles, and that's how you're counting your R. So the first circle would be 1 out, second circle would be 2 out, 3 out, etc. So you have to kind of get involved. I mean, it's kind of intricate in terms of how you're counting, but that's the general idea. And so if I wanted to, I could plot a point on here, and let's say that the point is going to be 10 pi over 6. Again, notice you're dealing with r followed by your theta. This could be degrees or radians. Notice 10 pi over 6. What you're doing is you're going to the pi over 6, which I like to start with the angle, and then I'm counting 10 circles out. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That point right there is going to be right here. And labeling these in the polar graph can get a little bit tricky because of all the lines involved. So I think I'll just letter coordinate this. So I'll just say this is point A and this is point A. I'll make it a little cleaner. So at this point, we know that I can graph that. It makes sense. I could also do, let's say, B, which is 10, 180 degrees. If I go 180 degrees 10, I do the same thing. I'm going this way at 180 degrees. I'm counting 10 out. And so that is going to be right there, which would be B. All right, it's not so bad right now, but you can also figure that you can have negative angles and negative R's. And that's when things get a little bit tricky in terms of graphing. So, for example, if I had a negative pi over 3, let's say negative 4, negative pi over 3. That all of a sudden becomes a little bit more challenging. So the first thing that I'm going to do is do the angle. So negative direction, same idea. You're going negative. That'd be clockwise. So this is going to be pi over 3 down here, or you could say negative pi over 3. But then the directed distance is a negative 4. Negative means going away from the angle. Meaning instead of going toward the angle, I'm going to go away from the angle. So really, this point here, point C, is going to be going 1, 2, 3, 4, which is right here. So we see that with negative r's, all you do is go away from the angle. That's the only thing you really have to remember. That's the first part of the homework, is to simply graph the points. The second part of the homework is they're going to say, all right, I'm going to give you a point. And let's say the point is, well, D, which is 8 pi over 3. Okay, that's not too bad. I'm going to go to pi over 3, and I'm going to go to 8, which is 2 in from 10, and that should be right here, which is point D. But then they're going to ask, what are the 3 other points that lie on the same exact point as D? In rectangular form, we only had 1 point. I mean, if we had a point 2, 2, there was only 1 point that you could list as 2, 2. But on this one, we can actually have 4 points that represent the same exact point, because you can have negative angles and you can have negative distances, which can bring you right back to that same point. Well, one distance could be, let's see, I'm just going to put 4 more up here. 1, 2, 3, and 4. One point is, instead of the positive direction, I go the negative direction. So I'm going to go here, go all the way around until I get to here. So that's going to be 5 pi over 3, negative 5 pi over 3. And if I do that, I still go the positive distance, which is going to be 8. That will hit the same exact point. Well, there's still 2 more. The key here, I believe, is we want to do the negative distance. So, in other words, instead of going pi over 3, I want to come down here and do the 4 pi over 3. Because I want to go to 4 pi over 3 this way and then back up to D on the negative r. So that means that this could be 8, negative 8, and 4 pi over 3. 4 pi over 3, negative 8 going away, gets me back to D. And then there's only one more. That last one is going to be where it's negative 8 and a negative angle, which is going to be a negative 2 pi over 3. 1 pi over 3, 2 pi's over 3. You're going negative direction here, comes to here, back in the other direction is going to be negative 8. You can see how that can be a little bit challenging, and this is just the basics of putting points on a graph in polar form. We're going to get into putting equations on the graphs, and you're going to have to be able to graph all these points and make equations out of it, which is going to get tricky. All right, so feel comfortable with plotting points on a polar graph. Next, the next part of the assignment is going to be to convert between polar to rectangular and rectangular to polar. So let's go ahead and do those two ideas and see what we're looking at. Now, there are two ways of doing this, and you can pick whichever way you feel comfortable with. One way is to draw it and figure it out on your 30, 60, 90, or 45, 45, 90, or on the axes. The other way is to actually use an equation to convert. Now, I find it much easier to draw it and work around your special right triangle. If you can do that, you're way ahead of the game. Let's go ahead and look at a couple examples in doing this. Let's say I want to convert from rectangular to polar. And when you think about this, I find it easiest to think about, I want to take my x's and y's and convert them into r thetas. I want to get rid of all xy's and replace them with r thetas. So if I had a point, let's say, that was a rectangular point 4, 4. And I want to convert that to my r theta. Well, one way to do that is to graph it. So I'll say, okay, I want to do the graph. I know what 4, 4 looks like. It looks like this, where I know my x and y is 4. And then what I really want to do is figure out, well, what is my angle, theta, and what is my directed distance, r? Well, that's pretty easy to see. Your theta is going to be 45 degrees, or pi over 4 radians. And your r is going to be 4 square roots of 2, because you multiply by radical 2 to get to the hypotenuse, and you're done. Easy. Well, let's say you don't like to do it this way, but you want to do it the other way, which is to actually use your identities, your equations. Let's see if we can figure that out. Well, I know that x squared plus y squared equals r squared, so 4 squared plus 4 squared equals r squared. R is going to equal 4 square roots of 2, if you want to do it that way. And you can also say, well, I know that the tangent of theta is equal to 4 over 4, which means tangent theta equals 1, and I know the inverse tangent of 1 is equal to 45 degrees by looking at my table. This is the work you could do, or the other way is just to see that this is 4 square roots of 2, and then that's going to be 45 degrees. You can see how much work difference there is, and I think a visual is a lot easier to work with than equations. It's up to you on which one you want to choose. Well, you can do that for every one. You could also do it, for example, if you took the same problem and you wanted to convert, let's say, -3, 0, which is rectangular. If you think about what that means, you're talking about that point right there at -3. Well, that's easy to see what the polar is. The polar is going to be, let's say, radians here, pi radians, and then it's going to be a distance of 3 away from the pole. So you can do it on the axes, you can do it off the axes. Still not too bad in terms of going ahead and doing that. A lot easier than going through this, but again, that's up to you. The other part that you have, the last part in your homework, is to go from polar to rectangular. And to go from polar to rectangular, you're going to focus on our theta going to xy. Again, what I would do is I would graph it and then see what you're looking on the graph. So let's get a point here, and let's say it's going to be 10 pi, let's go 5 pi over 6, make it interesting. and I want to go ahead and put that in XY form. So first of all, I want an example of where that is. Now, I could do that on here. Well, the 5 pi over 6 is here, and let's say that this point right here is 10. So this is what I'm looking at. That is 10 right here. This is going to be my reference angle, or pi over 6. If I look at that triangle, because 5 pi over 6 gives you pi over 6 left to pi. And then this is my pi over 3. So I know that here's my 30, 60, 90 triangle, meaning 10. This is my small side opposite to pi over 6, which is going to be 5 divided by 2. And then this is going to be 5 square roots of 3 multiplying by radical 3, working away around the 30, 60, 90 triangle. That gives you your answer. You're done. The only thing you have to remember is your x is now negative 5 square roots of 3 because it's negative direction, and your y is going to be 5, and that's all it is. If you know, again, your 30, 60, 90s, your 45, 45, 90s, doing these problems is easy. If you don't want to do it by drawing, again, that choice is yours. Let's see if we can figure out how to do it the other way. Well, let's see. We're going to have, what do we know? We know the r's and the thetas. So I know that x is equal to r cosine theta. X is equal to 10 cosine 5 pi over 6, and y is equal to 10 sine 5 pi over 6. R sine theta. And if you evaluated these with reference angles as well, you're going to see that the cosine is going to be, let's see, well, let's go ahead and do this. Cosine 5 pi over 6, meaning if I were to draw that, I'm looking at this, and this is going to be pi over 6, so I know that that's going to be negative, so that's negative cosine pi over 6. It's negative because of the SATC, or the Santa Claus, and therefore x is going to be equal to 10 times a negative square root of 3 over 2, which is equal to negative 5 square roots of 3, which is the same thing as I have up here. Similarly, y equals 10 times positive 1/2, which is going to equal 5, same thing as I have up there. Pick your method and stick with it. Today we're going to learn about the graphing of the points. We're going to be looking at converting, and then soon we're going to be looking at equations and graphing them, or converting equations and then possibly graphing equations. All right. Work with the 30, 60, 90s. Again, I would suggest to you that it's a lot easier to work within your special right triangles than to work with those equations.